Hello, welcome to the class ECE317 Digital Signal Processing. Last time we introduced the method how to restore a signal from the samples. Today we will keep working on this problem, but we will consider different situation. All right. This is a ECE317 for the 10th week Friday's class. It's weekend again, Friday again. Okay, we have two sides actually, right? The first side is take samples. So we start from XC of T. Then we can have analog to digital converter or CD converter. Yeah, same meaning actually, but you need a time t, right? Step t. Every t you take sample, this side you will have x of n. This is a discrete time signal, which is xc of t, but t is n times that capital T. Alright, this is a time domain. And what happened in frequency domain is this one, we suppose this has a spectrum xc of j omega. Then this side we will have x e to the j omega, which will be 1 over t times the summation of those xc, j times omega, but now it's shifted omega by 2k pi and also scaled by t. We have this. If we give graph, it will look like this. Look like this. Every 2 pi, 4 pi, negative 2 pi. Every 2 pi we have a copy of this one, but not original copy. We need to do some scale, right? Do some scale. If here's a peak value is a, here the peak value will be a over t. And if this point is omega n, and this point will be omega n times t. Right. Here we suppose t is smaller than pi over omega n, and pi over omega n is called Nyquist sampling step. Right. Okay, so this is one side. We start from a continuous time signal, then we take samples. And then we discussed how to restore. We have x of n. Then firstly we create a continuous time signal, which you denote as xs of t. It is a summation of x of n times delta of t minus nt, and run from negative to positive infinity. Here we need that step t. So this is a sequence of number x, right? X of n is sequence of number, and here's x as of t is a function of t. T can be negative to positive infinity, but this function only contains some impulse, sequence of impulse. All right, we use these, go into a field h of j omega. Then we can have xr of t. Actually, this xr will just equal to that xc of t. Now, of course, we need a requirement. The original signal is band limited signal, right? The band is limited, and also t, you have to choose t smaller than the Nyquist sampling step. If you use t larger, then you cannot have this. Alright, you look at it like this, right? We can also have is to see what happened in the frequency domain. This one, the spectrum just look like this, right? So in frequency domain, x of n, that is x of e to the j omega. This one will be a sequence of like this way, right? Every 2 pi you have a peak. Every 2 pi you have like kind of peak. Then go to here for XS. We also have this one in frequency domain is XS of J omega, which is which one looks like this way, you know. It is still a sequence of sequence of these peaks, right? But the scale is same way as this one. These two they have same scale. So this point is omega n. Right? This point is omega n. And the center will be 2 pi over t. 2 pi over t. And the peak value, it is still t over a over t. A over t. Same with this. A over t. A over t. Right? Here is also a over t. And then what is the H? H will be this one. It is a low pass filter. Right? Low pass filter. Here value is t. Here is a pi over t. Here is a negative pi over t. This is a capital omega. This is the H of J capital omega. This is H. Then you use XS as input. Go through H. The output will be H times XS, right? You times these two together. You times this one and then with this one. You times these two together. This one, you know, only when omega is between negative to positive pi, it is a non-zero value t. Otherwise, they are zeros. So when you times these two together, you will only keep the center part. This is a capital omega, right? Only when capital omega is 0. This is a capital omega is 0. Only in this interval, you will keep this part, right? You keep this part, and all the rest, because the times 0, so they disappear. So this one, then we can have XR of J omega, which is H times XS, right? H times XS. It only contains this part. This is omega n. Here's omega. Here's So we get this one. This is same with this one, and here's a, right? Because this value here is t. T times this a over t. I get a. Peak value is a. So this one, they are totally same. Totally same. All right. Yeah, of course. Here we need the requirement, right? We need a t no more than equisampling step, and the signal itself is band limited. So under this condition, we can have this way to restore the original signal. Okay, now we consider the different case. The signal is not spectrum not looks like this, but is a band pass signal. Okay, now we consider a band pass signal. A band pass signal. Band pass signal. Okay, I still write it as XC of t. Then in the frequency domain, it looks like this. Like this. So here we have omega n and omega, which is just a notation. I want to separate these two. Okay, omega d. All right, omega d. This is a capital X C of J omega. Now it looks like this. So for this one, by take sample. Take samples. Then in frequency domain, what will happen? This omega, right? And I get X of n, and then I have XS of t, right? I can build this based on X of n times delta t minus nt, right? I can have XS, and XS in spectral in the frequency domain. This one, how will these look like? it will be copy of this one, original one, put it here, and shift it, right? So every 2 pi over t, we can have a copy of that. Okay, let me put the original one. This is a copy at the center t equal to 0. So just move it to here. Nothing change. Or change a little bit, the peak value changes. This will be, suppose here is a, the peak value is a, then this will be a over t, right? We change this. But here are same. Here will be same. This point is omega n. This point is omega d. Then I want the second copy centered here. Actually, this point is depending on the value of t. When t is large, this will be small. When t is small, this will be large. I choose this t so that when I put the second copy, I want those two peaks. One is here, one is here, symmetrically, right? I want one is here. This is in this empty place, right? The original one, I have two peaks. And in the middle, capital XC is just 0, so I have a gap. And here I want the second copy. I put this in the gap. Okay, so we choose t by this way. The value, this one, here's 2 pi over t, right? So this will be 2 pi over t minus omega d, right? And this one, this point will be 2 pi over t minus omega n. Right? I choose t like this way. Choose t so that this one happen. This one happen. By this way, you see, this is original part, right? This is original part. So we can restore the original signal by a band pass filter. Right? This is a filter, right? This is a filter, band pass. Previous one, this is a low pass filter, right? This is a low pass filter. This is a low pass filter. Now we try to use a band pass filter to restore the original signal. Okay, then how to choose the t? Of course, if you choose the wrong t, you cannot have this. The t, we want to have this, so we want this point and this point. This one should be smaller than this, right? So I need 2 pi over t minus omega d, smaller than or maybe equal. I just smaller. Okay, smaller omega d. Okay, this one is smaller than this one. And this point, this one will even smaller than this, right? No problem. But no more. It should be positive. Cannot go across this. So I want this is positive. So 2 pi over t minus omega n is this point. It should be larger than 0. So I want these two conditions. So that means this part, the most right side will not go across this point, right? This one will not go across this point, and the left side will not go across this original point, right? So this peak will be located inside this interval, right? So I have these two conditions. Then I want the condition on t. So this is a 2 pi over t smaller than 2 omega d. I can cancel the 2. Then I have t. I move t to that side. It should be larger than pi over omega d. So I need to choose t larger than this. And this one I have 2 pi over t larger than omega n, right? Then we have t will be value smaller than 2 pi over omega n. Okay, so we can choose t by these two conditions. Okay. Then I think any values between these two will be fine. They will be fine. Okay, we use this kind of t. Then this peak will be in this part. Okay. And if you use one more here, 4 pi over t, then this one will give us two peaks. One is here, one is here. So all these peak, they will not have alias, no overlappings. Then we can restore by a bandpass filter. Okay. Then so design bandpass. Consider I still have XS, right? XS of T go into I use a edge bandpass field. I put a B here. HB of J omega. This side will be XR of T, and I will say this one will equal to XC of T. And one they are same, right? Maybe they are not, they depend. Okay, so how to choose this B? HB of J omega or equal to, the value will be T or 0. Which part should be T? I want this part should be T, right? So I want well some okay, suppose this part is B, this point is A. So from A to B it will be this value. I want to restore A, so here's A over T, here should be T, so it's T. And here I want magnitude, the absolute value of omega smaller than B and larger than A, and 0 otherwise, right? I want this, and A is a value between these, between omega D, and A is a value between omega D and 2 pi over T minus omega D. Okay. And the B will be value between these 2 points, so omega n and 2 pi over T. Alright, so that depends, Now I just writing this way. If you know omega D, you know what is omega D, then you can, and what is omega n, then you can have the value. Now I just list it like this, and then similar in the time domain. In the time domain, this is in frequency domain of this capital H, right? In time domain, we have H of T. There will be this one. If we give a graph, it will look like this, right? From A to B, negative A to negative B, here's T. Looks like this. This one can be written as, 2 rectangles, right? I write this one symmetrically. From negative B to B is a rectangle. Then subtract second rectangle is from negative A to A, right? So this one will be a sink. Well, that depends. Sink something minus another sink. Okay, another sink. One sink minus another sink. Depending on the value of A and B. We have this. I put it here. Rectangle. If here's a pi over T, and this value is T. This is in omega domain, in frequency domain. Then we go to the time domain. See, continuous time, CTFT, continuous time Fourier transform. Do the inverse. This one will give us sinc or be T over capital T. And we have this one. Okay, so this one will give us this one. Then that A and B, yeah, you can just apply this. So here should be some coefficient here, and some coefficient here, depending on the A and B. For example, this if B is pi over 10, if B is pi over 10, then here you need a pi over 10. Then here you put a 10 here, right? And here's also 10, but now is a T. Then here you need to put some coefficient here, right? Yeah, that depends. I just write it this way, and then we can have what is XR? XR of t will be summation of x of k for all the k's. Here's times h of t minus kt. Alright, so we can restore the original signal in this case by a formula in the calculation in this way. In the filter way, analog way, you can build a filter, let signal XS go through it, you can have that. And this case, the sample step T, you see the sample step T is here. And what is the Nyquist sample step? Nyquist sample step is this one, right? Pi over omega n. I put it Nyquist sample step is pi over omega n. You see, now t is larger than pi over omega d. Omega d is smaller than omega n, right? Omega d is smaller than omega d is here. Omega n is here. So omega d is smaller. Then pi over omega d is larger, right? Omega d is smaller, so pi over omega d is larger. So this is larger than pi over omega n. You see? Now we choose a t. We use this t to take sample, and this t is larger than Nyquist sample. Nyquist sample step. Okay. So by this way we can use less samples, but we still can restore the original signal. Okay. Of course, this is just for bandpass signal. Bandpass signal. The signal XC has a spectrum looks like this. Between these two, they have a big gap of the frequency. Right? But in the real application, you know, almost all the signals we're using, they have this feature. Like the radio, you have different channel. TV, you have different channel. Cell phone also have different channel for different companies. All the channels looks like this. They have a certain band of frequency, and I think almost all the country they have the government. They have a kind of organization. They will distribute. They will manage these frequency band. They distribute different frequency band to different company. So they were not, they will not confuse each other. The different company, the different channel, they use different frequency, right? Yeah. So the signal always, in most cases, actually, looks like this. It's a bandpass signal. So for this kind of signal, if you want to take sample, you can use a sample rate. You have less samples, or use a sample step. The step is larger than Nyquist sample step. And for this one, we can illustrate by example. Okay, let me go to the MATLAB. So last time we have example, right? I still use that one. Let me go to the ECE317. Okay, I have, that is last time we have lecture 10 Wednesday's class, right? We have this one. Let me edit it. Edit this one. That means I open it and I save it as a different file for today's class. So this is a 10F. Alright, today is Friday. I just use the 10F. Alright, for this one now, okay, let me write down here. Example. We consider signal XC of t, which is 2 of cosine 10 pi t plus 3 of sine times sine of 7 pi t. Right, this is the original signal. And this one, what is a capital XC of j omega? Or see, it looks like this. one part in the 7 pi and one part in the 10 pi. We have two frequency components, 7 pi and 10 pi. So this one is just omega n. Last time, when we take sample, I just use this omega n, right? We just use this omega n, we take sample, we determine the Nyquist sample rate and Nyquist sample step, and we choose our step smaller than that, right? So Nyquist step, there will be pi over omega n. Now is 10 pi. Pi over 10 pi is 1/10, 0.1. So we will choose a sample rate, sample step smaller than 0.1, then that will be fine. But now we consider this as a bandpass signal. It has a band, right? And the inside part is nothing, it's 0. So we can have a band, and this is omega d. This is omega d. Omega d. Alright. So we take sample, use step, wave step t, so that we just have our estimated value of t will be here, right? We use this one. So that t was smaller than 2 pi over omega n and larger than pi over omega d. We use this t. We choose the t, use this. Okay, what are these? Omega n is 10 pi. And omega d is 7 pi. So this is a 1 over 7. 1 over 7. 1 over 7. Okay, this is a 0.1429, smaller than t, smaller than 0.2. So we can choose a t in between these two values. Now we can just use t. Which t is better? Use 0.16. Alright, 0.16. We use this one, 0.16 between these two values. We just use this as a t as a sample step. Then what will happen? We take sample t. Now t is a 0.16. Okay, I use this t, and here I have a restored signal, right? As restored signal by this equation. Actually, it is related with a lower pass filter, right? If I do the same thing, still use a low pass filter, what will happen? Just run it. You see, the original signal, we take samples. The figure 1 is the original signal, and those circles are the samples. Now we restore it by a low pass filter. You can see some details was lost. Actually, the result signal looks not so similar. Actually, quite different with the original one, right? Okay, so now we choose the bandpass filter. We use a bandpass filter. Which kind of filter we can use? Now, to restore XC from XN, where XN is XC of NT, right? Is this one. So to restore this one, we work like this. Work as follows. We have xn, then we need to have xs of t, which is x of n times summation of x of n for all the n's, xn times dirt of t minus nt, right? T will be given, and then we use this, go through h0 of j omega. It's a bandpass filter. Then we can have xr of t. And what is h0? it will looks like here, right? And this value will be t, and these two, what are these two values? You see, we can choose B and A between at least two location, right? Two location to cover this part, but not too much. This B will not go over this 2 pi over t, and this A will not go over this point. Alright, so here the thing is this one, right? So we need to choose B here, we choose A here. So the center here is and give more details. This is a XS of J omega. It will still contain these 7 pi and 10 pi, the original spectrum of the original signal, right? The spectrum of original signal. And now, because t is given, t is 0.16, right? So I want this will be 2 pi over t. This will be 2 pi over 0.16. What it is? Let me do a calculate. 2 pi, 2 over 0.16. I get 12.5. Okay, this is 12.5 pi. Alright, so it should be here. This is a 12.5 pi. And center at here. Then we will have a copy of the original spectrum with this as center. So you see, the original one start from 0 to 7 and 10. Now we'll start from this 12.5, we'll go back 7 and 10. So go back 10, I have 2.5 pi. I go 7 back, I have 5.5 pi. Okay, we have these two. So we will choose A here and B here. So A's value between 5.5 to 7. So we can use which one is better? We can just use A equal to 6 pi, for example, right? 6 pi is between these two values. And B we can use between 10 and 12.5 pi. I use 11 pi. Alright. Okay, we use these A and B. So here will be 11 pi. Here will be 6 pi. Sorry. Yeah. I didn't show the graph. Yeah. I need both. Right, 12.5. So this point is 12.5 pi. And then we need to go back. Right? This is original spectrum. Now we need a copy of these to here. So from here I need to go back to go back tens, right? Here's a go from to 10. So here we'll go back to 10. Here go back, this is negative 10, right? Go back to 10. So 12.5 go back to tens, get 2.5 pi. And here this one is a go back, this is a negative 7 pi, right? Go back 7. So 12.5 go back 7, I get a 5.5 pi. I have these. Then I will choose A between 5.5 and 7. I choose A here. And B will choose between 10 and 12.5. So I can just use A is between these, I choose 6 pi is good, right? And between 10 and 12.5 I use 11 pi. Okay, now you can have different choice. Alright, not unique, but here I just choose these two. So this is a 11 pi here and 6 pi here. Then what is h of 0? It is just like this. And of course you can realize these if you want to build a circuit to do it. Now in the computer we do the similar thing. We want to find h0 of t. We find these, and the result will be xr of t will be summation of x of k times h0 of t minus kt. K run from negative to positive infinity, right? We have this one. HR will be this. And H0, this one we can consider is a rectangle minus rectangle, right? Two rectangle. One rectangle from negative 11 pi to positive 11 pi. Second rectangle from negative 6 pi to positive 6 pi, right? So the larger rectangle minus smaller rectangle, then we have H0. Then H0 in time domain, it will be some subtraction of two sinc functions. Sinc function minus another sinc function, minus another sinc function, looks like this. Okay, we need the coefficient. Let me write here. We know this one. If here's a t, here's a pi over t, this rectangle in the frequency domain, we go back to time domain, okay, continuous time for the transform, do inverse. This will be sinc of t over t. Is it like this? So that pi over 11 pi equal to pi over 1 over 11, right? And if here is 1 over 11, this gives us sinc t over 1 over 11. Okay, we have this. But now the peak value here should be t, right? H0, here's t, here's t. So this point will be 11 times 11t, right? So you get t, that is t. So here you need a times 11t. 11t. Okay, so this is a rectangle related with 11 pi. 11 pi. Okay, 11 pi. And that 6 pi. 6 pi. Here's a t. But t, I write this as 1 over 6 times 6t. And this is a pi over 1 over 6. Okay. This will give us, okay, sinc function t over 1 over 6. 1 over 6. If here is 1 over 6. But now I need 6t more. Alright, this is a, then we have H0. H0t will be this one minus this one. So it is, okay, I put t in the front. It is 11 of sinc function 11t actually, right? 11t minus 6 sinc function, this is 6t. This is a, looks kind of strange. Alright, it is this one. We have H0 is this one. Okay, and the t is 0.16. Okay. T is 0.16. So we have H0 looks like this. Looks like this. Okay, then we can put them in the program. I take sample, use t equal to 0.16. These are samples, nothing changed. Okay, I can plot both. And here, okay, when I restore this sinc function, I will change. Sinc function will be t times, inside will be 11 times the sinc function. 11 times the sinc function, and another is minus 6 times the sinc function, right? And inside the sinc function will be, the first one is 11 times t, and the second will be 6 times t. Oh, is it good? Looks kind of a strange one. Okay, let's just try it. Anything else? Do we need a change? Okay, there we are. Run it. Something wrong. Yeah. Okay. Let me see. I need a. Let me go back to here. 11 pi. 11 pi. And this is a pi over t. Here's a t over t. And 11 pi is pi over this one. So this is a t over this. Oh, I didn't minus k. Sorry. Minus k times t. I forgot this. I need to shift it. Minus k times t. I need this one, right? And here is also I need a t minus k times t. Alright. I need one more of these. Oh, okay. Now it's good. You see? Yeah, now it's good. The figure 1, this is the figure 1. Figure 1, actually, they are the original signal and the symbols, right? Original signal and symbols. And the figure 2, we also have the symbols, and we have XR, right? XR is the restored signal. So you see, they are same thing. So we can restore the original signal by these symbols. And when we take these symbols, we use a symbol step t, which is larger than the Nyquist symbol step. Yeah, this is larger than Nyquist symbol step. Nyquist step here should be 0.1, right? We have 60% more. You can think this will save you the amount of data by 60%. That's a lot, you know. Yeah, you can transfer for example, think you can have some quality of the maybe music, maybe images, but you can use less data to transfer the same image or same music and keep the same quality, right? Yeah, so the things like that. All right, but of course this is a case when the signal is a bandpass signal. The spectrum looks like this way, right? XC in frequency domain looks like this. Then you can try to use a t larger than the Nyquist step, and of course this space will be enough to put one peak here, right? You can put a copy of this in this place. This space is large enough. If this here is very narrow, it's not enough to put this one, then you can't use this method. All right. Okay, that will be all for today. And yeah, I have 6 more minutes, but it's fine. I do not have anything to talk about right now. If you have any question, you can go to the office hour. The Monday this is 3/17 on a Monday. It's a Wednesday. Every Wednesday I have office hour. Right? You can go to office hour. Then now that's all for today. That's all for today. So see you next time. Bye bye.